Good morning, everybody. We'll get started in a moment as people roll in. We'll give it just another minute. Okay, why don't we get started? Well, good morning again. Welcome to today's Future Supply Actions Funding Program webinar. My name is Warren Teitz. I'm a team manager within Water Resource Management within Metropolitan, and I'll be your moderator for today. Next slide. Uh-oh, we're not. There we go. Program for today is just some welcome and some short introductions, followed by the presentations, and hopefully we'll have some time for Q&A. We are some housekeeping items first. We are recording today's webinar, so your microphones are muted. If you have questions, please type them in either into the Q&A in the chat, and we'll get to them. We do plan on ending at 10:45. We value your time. Hopefully we will have time for questions. We plan on putting the webinar recording, the slides, and the final report all on our website in the near future. Next slide, please. So most of you know who Metropolitan is. We're the nation's largest wholesale water provider. We serve 19 million people, a $1 trillion economy. We sell our wholesale water to our 26 member agencies shown here on the map. And we import water through our Colorado River Aqueduct from the Colorado River and also from the State Water Project from Northern California. But we do a lot more than that. Next slide, please. Over the past 30 years, we've been diversifying our resource portfolio through investments in conservation, local resources, storage, exchanges, building flexibility into our distribution system. And I think we're up to $1.5 billion with Metropolitan's investments, and our member agencies have invested many billions more. Innovation in local supplies is key to the future as we advance our One Water approach. These local supplies help build resiliency to climate change into our portfolio. And this is where our Future Supply Action Funding Program fits in. Next slide, please. We established the Future Supply Action Funding Program with our 2010 IRP with the goal of driving innovation in local supplies. And through the program, we want to collaborate with our member agencies to pilot new approaches and demonstrate new technologies. And so, water agencies by our nature, because we have 19 million people and billions of dollars of infrastructure under that we're responsible for, we need to de-risk these new approaches and technologies, and these pilot tests and studies are how we do it. We want to remove barriers to local supply development. That includes technical barriers, institutional barriers, and regulatory barriers. And finally, the studies that we fund under the program benefit the local agencies that do them or that promote them, but they also benefit the region, and that's a core principle of the FSA program. And this webinar is how we get the word out and get the information to the people who can use it. Finally, the Future Supply program covers 4 local resources: groundwater, stormwater, reuse, and desalination. And this particular study is on brackish groundwater and the challenges associated with that. Next slide, please. So we've invested about $4 million in the current round of FSA studies. That includes $3 million for 14 member agency studies, and also just under $1 million with the Water Research Foundation for 6 potable reuse studies and 1 agricultural reuse study. So most of the member agency studies are wrapping up right now, like this one that we're about to talk about. And 2 of the Water Research Foundation studies have wrapped up, and the others are in process. And we've had 6 or 7 webinars so far, and we've got a few more scheduled throughout the year. Next slide, please. At this point, I'd like to turn it over to Jeremy Crutchfield from the San Diego County Water Authority, who's our member agency partner for this study, who will introduce the study and the speakers. Jeremy, take it away.
Great. Thanks, Warren. And before I get into the introductions, just want to thank Metropolitan for initiating this program. Very important for our region to be looking at these innovations and opportunities within Southern California. Also want to thank our agreement administrator, Ariba Syed. She has been very helpful throughout this whole program. We actually had a pretty significant scope change early on, and it was just a collaborative process with both the Olivenhain team and also Ariba and Warren to initiate that and make sure we were creating a project that was really beneficial for the region. So thank you to Met and staff for the assistance there. Now, just to introduce the speakers for today's session, Joey Randall is the Assistant General Manager for the Olivenhain Municipal Water District. We also have Don McFarland, Principal at DLM Engineering, and Brian Villalobos, Principal at Geoscience. So with that, let's go ahead and kick it off, and I'll transition it. Don, why don't you take over from here?
Okay, thank you, Jeremy. Can you guys hear me all right? I'll assume so. Yeah, so this is in brown there, you see the outline of Olivenhain Municipal Water District. On the left, the services we provide. So the district lies primarily between I-5 and I-15, just as east of Encinitas in San Diego County. Next slide, please. Some data about Olivenhain. Currently, we're delivering about 18 million gallons a day to our customers, potable water, that is. Don't have any local resources except for we recycle every bit of wastewater that's produced within the service area. Next slide, please. So everyone on this call, I'm sure, knows water in California. Metropolitan and the Water Authority do a great job on imported water and reliability. And they also do a great job on supporting local supply development, which is really what this is all about, the Olivenhain study. Next slide, please. So in 2015, 2016, we got a grant from DWR and went through a feasibility study. Geoscience was the lead on that project. And these are the steps we went through, looked at availability of groundwater, the quality treatment options, did some conceptual planning and cost estimating, and compared to our other options. Next slide, please. And the key findings were that the project is feasible and sustainable at 1 MGD or more, competitive with imported water, less than desalinated seawater. The blob that you see there, the orange blob, is kind of the general well field that we're looking at along the San Dieguito River. We intentionally kept it non-specific, can meet drinking water regulations. One interesting part of this was we had a lot of options for brine disposal, including agencies in San Diego County that have discharge permits for lagoons, coastal lagoons. There's also the ability to inject water near I-5. We had a great meeting with the regional board here in San Diego, and they really gave us some good guidance on this and really recommended that we use an ocean outfall. And that's their preferred and would be the best option for us. And also confirmed that our project was consistent with their vision. So because of the feasibility, we went into test well construction. That's what Geoscience recommended as the next step, a 1-year pump test. So again, I'm sure you're all familiar with well construction. The thing that's interesting here is the sound walls, about 20 feet high around the well. Did that for 2 reasons. One, to shield the local residents from noise, and we're right next to the San Dieguito River, which is habitat. So we shielded the birds also from the noise. Next slide, please. Again, enlarged and constructed the well. I'm sure you're, again, familiar with these processes. Next slide. Did a complete pump development and pump test analysis. Next slide, please. And that led us then to the long-term pumping test. And with that, I'll turn it over to Brian Villalobos to describe that work.
Thank you, Don. You can go ahead and go to the next slide. So what we'll talk about now is just what the results were of the long-term pump test. But I just wanted to briefly say that this stage of the work was actually the third phase. Initially, we were looking at a water budget for the basin using empirical data. Then we constructed a groundwater model, which I'll talk about in a minute. Calibrated it to see what the water budgets would, how to refine those water budgets for the basin. And then lastly, we wanted to stress the aquifer through a wet and dry sequence, an entire year, to have a given stress on the aquifer so that we could then back in to see what the differences might be in our water budget assumptions moving forward. So move to the next slide, please. Thank you. So again, these the wells that are shown here are the observation wells that we've used for the 1 year long pump test, and each one of those hydrographs we'll get into in a second. But also just to know that there are existing pumping wells, and so part of the project is to understand how much of increment of water would be available to develop even as a brackish source, but still not harm the folks that are already in the basin pumping. Next slide, please. So again, the wells that were actually influenced by the test well pumping are shown on this diagram. So Surf Cup 2 well, Surf Cup is an actual is an existing well that was used by the Surf Cup facility there, but it was shut down during the pump test, so we could use it as a monitoring well. And then also the three other green dots, the two up where it says Morgan Run P11D, Morgan Run test well, they're almost on top of each other, but we put transducers in those just to see if those would be influenced, and of course they were. Next slide. So here are the hydrographs of the wells that were influenced by the test well pumping. The green vertical line is the beginning of the pump test. So you can see once that just to the right of the green line, immediately those wells responded. So when the well was turned on, the water levels in those wells begin to decline a bit, showing that they're under the influence of the pumping well. The blue, the light thin blue lines at the bottom are preset rainfall during the period of the test. You can see that those water levels do respond to a rainfall, even though these are primarily in the deep aquifer, and I better talk a little bit about that in a second. There's a gray bar on that, and that's represents Lake Hodges releases. So during this period after the heavy rainfall in early April, Lake Hodges, there was water released from the dam, comes down through the gorge, and then into the forebay or the main recharge zone of the basin. And you can see it had an effect on the water levels. We had a shutdown. There was a leak in a pipe. We fixed the pipe, started the pump back test up. Then the center to the right hydrographs show the dry season, show the summer season. You can see the water levels respond during the dry season. And then after the rainfall in November, they begin to increase. The red line is when the pump test was shut off, and the sloped lines just to the right of that red line are the recovery of those wells. Go ahead, the next one, please. So these are piezometers now, observation wells that are in the shallow. So I didn't tell you that the San Dieguito basin is like pretty much like all of the coastal basins along San Diego County, that you have their shallow river, riverbed type aquifers. The basins are shallow. They're fairly they're not that wide. However, there's been significant production over the years historically. So there's an upper aquifer separated by a lower aquifer by a pretty significant silt and clay aquitard. So these piezometers are screened in the above. So this is from ground surface, essentially, where water levels are shallow down to the top of that clay bed. What we see here is that the shallow well showed absolutely no influence from the pumping that was taking place by the test well, because it's screened only in the deeper part. Next one, please. And this also are piezometers that are near to the existing pumping wells. The black line is the Morgan Run P4D. In other words, it's a piezometer in the deeper part of the aquifer. D stands for deeper. And so is the pumping wells in the golf course. And in the black line, you can pick up the operations of the golf course wells very, very clearly. So we're able to see where the golf course wells were running. They're influencing the piezometers there. Go ahead, next one, please. So the other thing is that water quality. So we were looking in the early stages, we were looking at iron and manganese, and that is the pink and the green zones. But also the orange is TDS. And you can see essentially the entire basin is brackish, from as much as, almost 6,000 TDS down to some parts, some parts 1,800 TDS. So everything in that basin at this point is brackish. It's a little more, it's more brackish as you move downstream, and it's likely reflective of historical seawater intrusion from agricultural pumping, but also there's some thought that the basin geology contributes to that TDS. But the entire the basin essentially is brackish. It's non-potable, and so this project makes complete sense from that standpoint. Next slide, please. And I guess this goes back to Don, and I'll shut myself off.
Okay, one of the things that we did during a pump test was take water out of the test well. We knew from historical records there was high levels of iron, manganese, and arsenic naturally occurring, as it does in many of the region's groundwater basins. And as you'll probably all know, this is a health concern as well as a concern for the integrity of the RO membranes. So we did test 2 filtration media, Green Sand Plus and Mang Ox. Next slide, please. Ran 10 to 12 hours a day for 2 days in June 2020, tested the removal effectiveness, runtimes, chemical addition, and both technologies achieved the target removal levels we were looking for. We updated our criteria, including we then had more updated water quality information, and this obviously is beneficial to other agencies that are looking for this kind of treatment. Next slide, please. And I'll hand it back to Brian at this point.
Okay, thanks, Don. So the next part of the analysis was to take the data from the long-term pump test and update the groundwater model that was constructed in the previous several years. Next slide. So the groundwater model, the area of the watershed is shown in green. The black lines are the outside watersheds and also sub-watersheds that contribute to the San Dieguito Basin, which is shown in yellow. Let's go to the next one. So the model is a Monflow model that's with cell sizes of 50 feet by 50 feet, and the black rectangle is the edge of the model. Go ahead to the next one. So the San Dieguito Basin was built into 5 layers. Essentially, layers 1 and 3 represent the shallow and the deeper aquifers, and 2, 4, and 5 are essentially low permeability geologic units that are in the basin. And this was done by looking at the numerous well logs in the basin to be able to create a conceptual model that formed the basis for the groundwater model. Next slide. So for the groundwater model update, as a result of the 1-year pumping test, we refined the layer thicknesses based on the new drilling of the test well. We refined the aquifer parameters based on the pump test, the response of the wells that were nearby. Each one of those provided additional data for the model. We extended the model calibration period from 2001 to 2020. Previously, it was at 2016. We updated pumping tests for existing pumping wells. So during the interim period between the initial model and the start of the pumping test, we were able to gain more data about the local wells, which ones were pumping, how much they were pumping. So we were able to, again, to refine the model with the latest data. We added the test well pumping, as I said earlier, and then we reran the scenarios that we originally ran to look at what the water budgets would be. Next slide, please. So here again is the basin. The groundwater model had 41 target wells, and we had about 2,451 water level measurements that we were calibrating against. Next slide. So here are the calibration hydrographs. The blue lines are model simulated water levels, and the black dots and lines are the actual measured data from those wells. Generally, in general, they plot well. There are a few that are slightly off, like in 33 NC, but most of them plot quite well. Next slide. So the calibration statistics are here, and typically it's the bottom one is what we look at primarily. It's relative error is 6.8%, and the standard relative error that's acceptable is 10%. So we were below that. Let's go to the next one. So with that recalibration of the model, we then looked at an updated water balance. So let's go to the next slide. So these are the water balance components, obviously groundwater pumping, ET, evapotranspiration, a discharge to stream, mountain front recharge, the aerial recharge from rainfall, and the several ponds that are in the basin, return flow from applied water, stream leakage. Then the outflows, again, are shown, and then change in storage. So again, we're looking at how the basin has performed and what has been the long-term change in storage. So those are the water balance components. Next slide, please. So in 2017, we were looking at, the scenario included 2 well sites. So these are assumed well sites. Site 2 would be 500 GPM, and site 2A would be 500 GPM for a total pumping capacity. Now, again, this is a total additional pumping capacity in the basin from what we were already simulating from known pumpage, as well as knowing where where water demands were being met, apparently through wells. So the total pumping in acre feet was about 1,600 acre feet. So for the 2021 modeling, the test well was able to produce 200 GPM, and I'll talk a minute why it was that rate. So we added site 2 at 400 GPM and site 2A at 400 GPM to again come up with a total of 1,000 GPM or 1,600 acre feet. Go ahead, the next slide. So again, the reason why we had assumed these larger well capacities is historical data has shown that many of these wells, you can see in the center of the basin, say near site 2 and 2A, if you can see on your screen, Morgan Run test well produced 600 GPM, but it was essentially in the center of the basin. Western States Investments historical 600 GPM. If you go further north up and towards the forebay, you can see 1,000 GPM, 800 GPM. So we know that historically that wells in the basin can produce at rates up to 1,000 GPM. The test well was sited in an area that produced a little less, primarily because it was the available site to test was closer to the edge of the basin rather than being able to penetrate the full thickness of the aquifer. But we know, again, as the project moves forward, there are areas that can produce those results. Next slide. So the updated water balance is shown here. You can see 2017 calibration run against the 2021 calibration run in the 2 columns that are essentially in the center of the table. And then the 2017 scenario run, that's the 1,000 GPM pumping against the 2021 scenario run. So I think really all of the water balance terms are there. I won't go through each one, but essentially we see that in the calibration run, the change in storage with no project is about 130 acre feet. In the 2021 in calibration run, the change in storage was about a positive 110. 2017, after pumping 1,000 GPM or 1,600 acre feet, the negative change in storage was minus 260 acre feet. With the updated scenario run, the change in storage was a negative 150 acre feet per year. Now that represents approximately 1% of the groundwater storage. And again, the time frame that we're looking at for the 2001 through 2020, if you look at a cumulative departure from the mean, it's primarily a dry downward decline with a couple of peaks in between. So in the long run, it's very likely that under natural conditions, this could balance out. And again, minus 150 represents about 1%. Next slide. So again, these are the terms, water balance terms from both calibration runs, and I just basically walked those through. And if you have questions, we can talk about individual terms. Next slide. So again, the next steps. Dawn, is this you? I assume. I'll let you take it.
Yeah, so, you know, with these positive results from the pump test, the district is going to continue the feasibility assessment. So we got kind of an initial check relative to imported water sources and seawater desal. We're going to subject the project to a pretty thorough economic analysis, look at, you know, optimistic and pessimistic ranges of variables, do an independent check on the cost estimate, look at siting in the valley, do some peer review and sustainability review. That'll look at water rights and what's the best process for the district to secure a supply of water. Is that a Sigma process? Is it CEQA or something else? And this is all to provide information to the district staff and ultimately the board of directors through a couple of workshops. It's really decision support information so that they can make an informed decision on whether to keep going with this project or not. Next slide, please. And this is our schedule. If everything moves forward, then we'd be looking to pump water and create potable water in the late 2020s. Next slide, please. There's your contact for the project at the district. And I think we're ready for Q&A.
Wow. Great presentation, everybody. Don and Brian. So we do have time, plenty of time for questions, actually. Please type your questions in the Q&A in the chat. If not, I'll start peppering Don and Brian with the questions that we have, some softball questions. I am not